So you've taken probability before in many other years. We're now just going to use our set theory and figure out probabilities, and we're going to use our perms and coms unit and figure out probabilities of those. So it kind of uses previous units to figure it out as well. So here we have the probability of event A. We write it as P of A, which reads the probability of A. So this here is the number total. So if I was looking and rolling, like let's say I was rolling 2 6-sided dice, the bottom of that would be 36 because there'd be 36 different outcomes. The top is the number of A's, or whatever A happens to be. So an example of this would be determine the probability of drawing a king from a standard deck of 5 cards. So we have a probability of king. So on the bottom we have the number of total cards, which is 52. On the top we always have the number of whatever probability you're finding, number of kings. And how many kings are there? 4. And then you do 4 divided by 52 and it reduces to 1 over 13 or 0.08 as a hundredth. Or sometimes they'll say to the nearest percent. And in this case it would be 8%. So you have to read what answer it wants in what way. If it says to the nearest hundredth, my answer would be 0.08. If it said to the nearest hundredth percent, it would be 8.00%, which is weird, and they would never ask it that way. But to watch for percent or hundredth, right? If it says hundredth, we don't times it by 100. If it says percent, we take whatever our answer is and multiply by 100. All right, so here we have, consider an experiment of spinning an equally spaced triangular spinner numbered 1, 2, 3, and tossing 2 coins with heads and tails. So the spinner, it's why it says triangular spinner is it just means that each of those spaces are equally likely to land on. It's not like one space, the number 1 is huge and then the 2 and the 3 are tiny, right? If they do these, they have to be equally likely. So we have a spinner, which options for our spinner, remember when we do trees, we write what it is up top and then the options below, and then you get like a sideways tree, right? Not a vertical tree. Then the coin has, we're tossing 2 coins after that. The coin 1 has options what? Heads or tails. Then coin 2, after I spin the spinner of 2, I could get a heads or a tails on the coin. And then when I spin spinner 3, if it lands on spinner 3, I could also get a heads or a tails on that coin. Then we have coin 2 that goes off of the other ones. So I could spin number 1, get a heads on the first coin, then heads, tails on second. Spin 1, get a tails, then heads, tails on the second coin. And then same thing for the rest. So then we can list our possible outcomes. If you spun the number 1, then you could get the heads and the heads on the coins. Spin 1, and then get heads and tails. Spin 1, tails and heads. Spin 1, tails and tails. Spin a 2, heads and heads. Then 2, H, then T. 2, T, then H. 2, T, then T. 3, H, then H. 3, H, then T. 3, H, then H. How many different outcomes?
12.
Yeah, 12. Because of each of the 3 spins, you get 4 different ones, right? So there's 12 different ones. So how many elements are in the total sample space? 12. What's a faster way we could figure this out if we didn't want to actually draw out the sample space, which we draw the sample space out when it's probability because of what they can ask us after this. But if we just want the total, we would have the spinner. and we would flip a coin, and we would flip another coin. How many options of spinners? How many options are on the spinner? 3, and then the coin, and then the coin. So how many total? 12. So we can use the fundamental counting principle because we're picking one of each to figure out the total number, right? We've talked about this before when we were in perms and comps. However, it is nice to write out all the outcomes because if they ask us the probability of, say, at least one coin flipping a tails, then I would pick this outcome, bottom, this one, 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 and I'd say 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 12, right? Because I can physically see which one has at least one tail. Okay? So here it says, show how you can use the fundamental counting principle. Oops, here we are. Done. Now here it says, state the probability of obtaining a 3 and 2 heads. So we want the probability of a 3 and 2 heads. So we always put the number of this on the top. So how many of the spins have a 3 and 2 heads? How many options up here have a 3 and 2 heads? 1. It's just this one, right? So that's 1 out of total. 1 out of 12. Done. Now the next one is the probability of a prime number and exactly one tail. What's the total? That doesn't change. What's on the bottom? 12. Now, what's a prime number? Out of 1, 2, and 3, what are the prime numbers? 2 and 3. 1 is neither prime nor composite, right? A prime number is 1 in itself. So 1 can't be prime. A composite has more than 2 factors, which it doesn't. So our first prime number is 2, then 3. So we need prime number and exactly one tail. So that's why listing the outcomes is helpful because now I can physically go look for it. So I need a prime number, so it's either the 2 or the 3, even's my only prime number, and it has to have exactly one tail. So there's 1, 2, and then here, 3, 4. Do you see that? I can physically see the outcomes. That's why tree diagrams I told you when you did perms and comms. They're kind of useless in perms and comms, but they're helpful for probability, so you can actually see the outcomes. So it'd be 4 out of 12, which reduces to then we're flipping over. So example 3, a blue die and a red die are rolled. You don't have the blue and the red colors, but you can visualize it. The outcome 3 on the blue die and 4 on the red die can be represented by 3, 4. So we're always listing the blue die first, basically is what we're doing here for the outcomes. So let's fill in the array below. So we have to list our blue outcome first, then our red, correct? So I would have 1, 1. Then here I would have 1, 2. 1, 3. If you didn't have any different colors, it wouldn't matter because the blue ones come first, right? Then 1, 4. So whenever I toss a 2 dice, a 6 by 6 dice, I will always draw out the outcomes. If they talk to us about outcomes about like sums, what you could do is you could literally write the sum of each. So then this would be like, this first block here would have like 2 in it, then a 3, then a 4, because you'd be summing them up, right? So if it asks you about sums. But whenever it's a 6 by 6, you will always have how many outcomes? How many total? 6 by 6. 36. And why? Because dice 1 has how many outcomes? I should say die 1. Whatever. This one, and then it has 6, and this one has 6, so we get 36. You can also count them if you drew it up, right? There are 36. So here, this one wants us to determine, now if we actually draw the array, which takes a little bit longer, people will not get the question wrong. If people draw the array, I have about a 99.9% chance of them getting it right. And the ones who don't draw an array, it goes down drastically by what you probably get right. So we want the probability of the same number. Probability of same number. How many same numbers are there? 6. There's 1, 2, 3, 4, 5, 6. So the number of same numbers goes on the top, 6. And on the bottom is always the what? Total. So how many is that? Reduces to 1 out of 6. Now here we want an odd sum. An odd sum. So if you don't know, I just use a different color. I'll use yellow. For an odd sum. 1 and 1 gets me odd? No, gets me 2. 1 and 2? Yeah. 1 and 3? 1 and 4? 1 and 5 gets me 6. 1 and 6 gets me 7. 2 plus 1, 3. 2 plus 2, no. 2 plus 3, 5. 2 plus 4, no. 2 plus 6, 7. That's 2 plus 5, sorry, 7. 2 plus 6, no. 3 and 1 is 4. 3 and 2 is 5. 3 and 3, 3 and 4. 3 and 5, 3 and 6. 4 and 1, 4 and 3, 4 and 5. 5 and 2, 5 and 4, 5 and 6. 6 and 1, 6 and 3, 6 and 5. How many check marks is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So half of them. Now please write this out correctly. You have to write probability of odd sum so that they know. And it's 18 out of 36. An odd sum is a little easier because half of them are odd sums and half of them are evens, right? But what if I say sum of 7? Well, then you have to go through and find the ones that sum to 7. So it's a lot easier if you have the array in front of your face that you won't miss 1 or 2 or add a couple extra. So this is 1 and 2. Okay, we have odds and probability. So this is really the first part of the lesson that's actually new. The other stuff we could have done in junior high, and it would have been probability that we did there, right? But what is this? So this says here, 4 black counters and 5 white counters are placed in a bag. So you take 4 black counters, 5 white, toss them in a bag. I can close the bag up, it doesn't really matter. How many do I have in this bag? I have 9 total in this bag, correct? Now it says one of the counters is selected at random. State the probability that the counter selected is black. So if we do probability of black, and we can do B because they put a B beside it. If they didn't put the B beside it, you'd have to write probability of black. Or it could be blue, right? Or whatever. So because they have the B beside it, I can put a B. So we're going to put number of black over number total. I'm just doing this to prove a point. How many black are there? 4 out of 9. Done. So we're still kind of sitting in junior high a little bit. Okay, we want the probability of not black, and they said that we can use B prime for not black. So probability of not black would give me the number of not black over the number total. How many are not black? 5 out of 9, right? The events black and not black are called complement events because they're complements, black and this is the complement. We've talked about this before, right, in set theory? These are called complementary events. The sum of the probability of these two events is what? If I take the probability of black plus the probability of its complement. Let's try it out. So the probability of black is 4 out of 9. Probability of not black is 5 out of 9. What do you do when you add fractions? You have to get a common base. Common denominator, we already have one, right? So we just rewrite that base, and then we do the actual operations to the numerators. 4 plus 5 is 9, so you get 1. Which makes sense. 1 as a probability is 100 as percent, correct? So if I take two complement events and I add them up, I have 100% of what's sitting there. If I take not the blacks and add the blacks, then I have the opposites, add them up, I get the total, right? So if I do probability of, let's do 1. If I have probability of A plus probability of not A, I get 1. If I'm given the probability of not A happening, I can just go 1 minus the probability of A happening. So if I need the probability of not A, I can take that 1 minus the probability of A, and what would be left over would be not A, right? If complementary events add up to A, it's just moving it around. Then we're going to flip over. So we did this. Probability of black is determined by doing 4 over 9, 5 over 9. So if I want the probability of not black, I could have just went 1 minus the probability of black, which is 1 minus 4 over 9, which got me 5 over 9. So it proves that it actually works. It is less likely that a black counter will be selected than a non-black counter because there's less of them, right? So odds in favor and odds against. This is what's new. Paying attention so I don't lose you. If it says odds for or odds in favor of something happening, whatever comes after that word comes first. So if it says odds in favor of a black counter, then odds in favor, odds for means it comes first. Whatever comes after it comes first. So what comes after it? Black counter. So then this is a black counter, and this is a not black. So if it says odds in favor, whatever comes after it comes first. Now this one here, it says odds against. If it says odds against, it comes second. So if it says odds against a black counter, then black would actually come second, and not black would come first. So it shows it down here. Odds in favor of event A comes first. Odds against event A comes second. Do you see that? So if it's odds in favor, it comes first. Odds against, second. So this time A came second, as opposed to first. Okay? So here it says the two numbers in the odds expression always add to the total. So if you actually add these up, odds always add to total. This is very important. So if I added these odds up here, what's 4 plus 5? 9. What's 5 plus 4? 9. How many of the counters were there? 9. So your odds should always add to total. So if we want the probability of event A, we can take A over A plus, not A, the complement, because A plus the complement add to total. So here it says the odds in favor of a white counter. So odds in favor of a white counter. So what comes first? White or not white? White, because it's odds in favor. So white would come first, and not white would come second. What is white? How many of them are white? 5. And then not white? 4. And here we have odds against a white counter. So what would come first? Yeah, the not white would come first, and then white. So we would have 4 to 5. Something to note, even odds are when the odds for and odds against are equal. So when you get a ratio of 1 to 1. So if my counters, if I had 5 blue counters and if I had 5 blue counters and 5 red counters, they'd be 5 to 5 odds, which is 1 to 1 when you reduce it. So when you have the same amount, it's equal or even odds. So here we have this. After suffering a severe heart attack, Dudley's doctor told him that he has even odds of making a full recovery. So he has even odds. So his odds would be 1 to 1. So what's the probability he makes a full recovery? 50. So the probability of a full recovery is 0.5 or 50%. If I write it as a decimal, it'd be 0.5, right? But as a percent, it's 50%, because it's equally likely. So example 3. Bailey holds all the hearts from a standard deck of 52 cards. So not all the cards, right? Just 13 hearts. He asks Morgan to choose a single card without looking. So the key thing here is our total is 13 hearts, not 52 cards. Right? We're just looking at 13. We pulled the 13 hearts out and we're holding them. Right? So here it says odds in favor. Whatever the heck comes after that comes first. Right? So odds in favor of choosing a face card. We agree? So what comes first? Face cards, because it's odds in favor of a face card, right? So face cards comes first. 2, not face cards. Odds are always complements. So if the one is face cards, the other one's not face cards. How many face cards are there out of the 13 hearts? 3. So it would be 3 to what? Not 3 to 13. 3 to 10. Because what do our odds always add up to? The total, which is 13 in this case. Okay? So odds always add up to total. So what about this one? The odds against, whatever comes after that comes second. Odds against a face card. So where does face card go this time? Odds against face card. First or second? Second. And then what would come first? Not a face card, just its complement, right? So this 3 to 10 is now just 10 to 3. It just switched it around. And what does 10 and 3 add up to? 13, which it should add up to the total, right? Now probability, you have to watch yourself. Determine the probability he will choose the face card. So probability of face card, what goes on the top in the numerator? How many? 3 over, what's our probability always over? The total. So technically, it's over the 3 plus 10. If you're ever given odds, it's whatever the one is over the 2 of them, right? Because the 2 of them added up give you the total, correct? So it'd be 3 over 13. Then this one, the probability not choose a face card. So probability of not a face card. How many not face cards are there? How many of them are not face cards? 10 out of the total, which is 10 plus 3, right? So it's 10 out of 13. Before we move on, I want you to do this one. Odds in favor of rain is 6 to 5. I want the probability it will rain? Try that one out. Odds in favor. When I say odds in favor, whatever comes after that comes what? First. So odds in favor of rain means rain comes first. And what's 5 represent? Not rain. And then I go off to the side and I go total equals what? 11 every single time. If you go do this, you will not make mistakes. Total equals 11. So I want the probability it will rain. So I'm going to write it out as probability of rain. So what goes on the top? However many times this happens. Well, how many times does rain happen? 6 out of 11. Done. That's it. That's all. Not a hard question. If you don't understand odds in favor and odds against, though, you have a 50-50 chance of picking the wrong one. And some people will give me 5 out of 6. That'll also be an option, which is not good. So. All right. So here we have a computer randomly selects a university student's name from the university database to award a $100 gift certificate for the bookstore. The odds against selecting a student who is male. Which one of these is male? 43. And which one of these is not male? 57. Determine the probability that randomly selected university student will be male. So before I even move on, I will always go over here and I'll say total. What's my total? Two added, right? What's the probability of male? 57 or 43? 43 out of 100, or 0.43. Because it doesn't ask to a percent, we don't put it to a percent. You have to watch, because some people get the right answers and then just do the wrong thing. So if it says to the nearest whatever percent, make sure you times it by 100. Okay, you guys are trying example 5 and 6. This one says, suppose the odds in favor of an event are 5-3. So odds in favor of the event happening, right? So this would be event. This would be not the event happening. Is the probability that the event will happen greater or less than 50? So probability of the event, how many are, what is the chance of the event happening? How many? 5 out of total? 8. Is that higher or lower than 50%? Higher, because 4 out of 8 would be 50, right? So the probability the event will happen is greater than 50%. What is this one as a percent? What's 5 divided by 8 as a percent? 60, pardon? 63? 62 point what? Someone said 62. 0.5? If you put 63, you're totally fine. It wasn't asked to round, right? You were just showing that it's higher than 50. Okay, this one here says, a hockey game has ended in a tie after 5-minute overtime period. So the winner will be decided by a shootout. The coach must decide whether Ellen or Brittany should go first in the shootout. The coach would prefer to use her best scorer first, so she'll base her decision on the player's shootout records. So, determine the odds in favor of Ellen scoring. So what comes first, scoring or not scoring? Scoring, because it's odds in favor of scoring, right? So scoring first, not scoring. How many times does Ellen score? 8 out of how many does she not score? 5. How'd you figure that out? Because the attempts are the what? Yeah, because the attempts are just how many times she tried, the total, right? Exactly. Determine the odds against Brittany scoring. So does scoring come first or second in this one? Second. And what comes first? The complement, which is not scoring. So how many times does Brittany score? 10 and then not score? 7. Here. Which player should the coach pick to go first? So we need to figure out the probability of them scoring, right? Because the best scorer goes first. That's what they're asking for. So probability of scoring for Ellen is how many out of how many? 8 out of 13. And what's that? 0.62. And then the probability of scoring Ellen. Why is that? That just sounds dummy. Ellen scoring. Ellen scoring. And then Brittany scoring is how many out of how many? 10 out of, which works out to 0 decimal. So who should go first? Ellen should go first, as she has a higher probability of scoring. And it says why. Okay. B. Josie is also on the team. She has scored twice in 3 shootout attempts. Should the coach put her in first? How do we figure out the probability of Josie scoring? What's it? Twice in 3. Oh. Yeah, 2 out of 3. Which gets us what? 0 decimal? So? Should the coach put her in first? Yes. The coach should put Josie in first, as she has a higher probability of scoring. Okay, example 7. A group of grade 12 students are holding a charity carnival to support I'm struggling, a local animal shelter. The students have created a dice game that they call BIM and a card game that they call Zap. The odds against, whatever comes after against goes what? Second or first? When it comes after against. If it comes after odds against, second. So odds against winning BIM. So this one is winning. This one is not winning. Right? And the odds in favor, odds in favor of winning Zap. Where does winning come? First or second? Odds in favor. First. So we've at least labeled them winning and not winning, right? The total here is how much? What's the total for this one? 7. What's the total for this one? 10. Okay, if Madison wants to play the game that she has a higher probability of winning, which game should she play? So we have to figure them out. Probability of winning BIM. What's the probability of winning BIM? Anyone know? 2 out of 7, which is, what is a decimal? 0.29. Okay. And then the probability of winning Zap. What is winning in this one? 3 out of 10, which is 0.30. So under a very slight margin, which should she play? Zap. Madison should play Zach as she has a higher probability of winning. Okay, and flip over. You try example 8 and example 9. Okay, so here it says when placing bets on horse races, the chance that each horse will win are often quoted as odds. In a particular 5-horse race, the odds against winning. So this one is winning on each one. And then this is not winning, right? Because it says odds against winning. So here it says determine the probability of the horses winning. So the probability of Free Spirit winning. Is what out of what? 1 out of 3. Please make sure that you make it out of the total, and the total is always the odds together. They will give the answer 1 out of 2. It's wrong, but it'll be there because you get to pick way more than the correct. So 1 out of 3 is 0.33. Then we have probability of Willow winning. 1 out of what? 1 out of 4, which is 0.25, so still less than Free Spirit. The probability of Foxtrot winning. What out of what? 2 out of 9, which works out to 0 decimal. Sorry? 2. Then the probability of Gloria winning. 1 out of 8, or sorry, 1 out of 9, which is 0 decimal. And then the probability of Lucky Joe. He's not very lucky. 1 out of what? 1 out of 12. He's the slowest. He's like the grandpa of the bunch. What do we get? Okay. So which horse is the favorite to win? Which one has the highest probability of winning? Free Spirit. As it has the highest probability of winning. Now, if it asks you anything about which one is better than which, you always have to turn to probabilities. Odds are not an easy way to tell which one's better. Odds have to be converted to probabilities to always tell which one's better. And then what are the odds in favor of Foxtrot winning? 2 to 7, right? Just flips them around. Then here we have the probability of student passing a particular math test. So probability of passing the math test is 0.8. What's the probability of not? If you ever want to talk about odds, you always need the complements of events happening, right? So determine the odds in favor of a student passing. So what comes first? Passing, then not passing. How many passing are there? 0.80 to 0.20. They'll never have it like this. You can go 0.8 divided by 0.2 math enter if you'd like. They'll always have the reduced version. You can do it as a division, but then rewrite it as a number. What is it? It's 4, right? So it'll be 4 to 1. Because you can take both 0.2 out of each.